to Colombia, to California, and I've been lucky to see all the energy and all the effort in Latin America. Yeah, so far, I think the workshop has been incredible. We've had presenters from all over the world. Now we have an outstanding lineup. We have people from Peru, from Brazil, from Mexico, from Spain, from the US, from Panama, from Colombia, from Venezuela, and from Puerto Rico. And yeah, I know that if you miss it, you'll probably have FOMO tonight, so wait for all of them. The schedule, we're gonna have first 4 oral presentations, 15 minutes each. Then at 3:15 approximately, we'll have a small break for coffee, like 15 minutes. And then there are 9 more oral presentations until 6 p.m. At 6:30, we can all go for some beers in Tavern Midway. It's 2019 Boulevard Saint Laurent. If you're gonna tweet with the hashtag LatinX in AI. And for all the people that are volunteering, please check in with Laura, she's over there. And yeah, that's pretty much it in terms of the logistics. Is it ready?
They're turning on the project.
Okay, perfect. So I'll intro our first presenter, Gonzalo. Gonzalo Barrientos is a Peruvian graduate student, now from University of College London, UCL in UK. He received his BSc from Tecnológico de Monterrey in electromechanical engineering, and his MSc in machine learning from UCL. Just as a side note, for if some of you don't know, the Technological Institute of Monterrey is one of the top 5 universities in Latin America. And there's one stat that really struck me, and is that 71% of graduates in Tecnológico de Monterrey will start a company or a startup. Well, Gonzalo actually started a company a few years ago too, and recently he's been a mentor for Udacity. And today, he's gonna talk about non-synergistic variational autoencoder. Please, an applause for Gonzalo, and hoping we can get this set up. Thank you, Gonzalo. Well, let's just see which different countries we have in the room. How many people do we have from Mexico? Nice. I don't see anything. How many people from Peru? Nice. A lot of people from Peru. Colombia? Argentina? No? No Argentina? Ready? Okay, then no more tests. I guess Peru was the winner. There you go, Gonzalo. Thank you.
Well, good afternoon, everyone. First of all, I want to thank to the organizer, to the committee, to the Latin AI organization in general. It's been a pleasure to present my work here today. So, well, this work is as a result of my master dissertation at UCL. The name is Non-synergistic variational autoencoders. I think this doesn't work. Yeah, better. Okay. First of all, I want to talk about a little bit of representation learning, because this work is mainly about learning representations. So first, I want to start with the question why it's important to learn a representation. What I want to say about this is basically the success of machine learning algorithms in general depends mainly in the data representation, since this representation will capture the underlying explanatory factors of variation. So for instance, in deep learning, we see that each layer will capture all the abstractions in our data. So that is why one of the reasons why for example, deep learning works, because each layer will give me information about the space, about faces, about shapes, in general capture those abstractions. That is why it's quite useful. The problem with this setting is that basically deep learning, or any kind of deep learning setting, will overfit to a particular task. So basically, the representation will be biased to that task in general. So if we like learn a representation which is like robust enough, or which is like disentangling these factors of variation, will generalize better to different tasks. So what is this thing about disentangling representations? So this disentanglement in general hasn't been defined formally yet, because it's like hasn't been like an agreement between all the researchers. But at least in my opinion, as well as my supervisor, we agree that disentangled representation should be factorized and interpretable. But what is exactly this means is that, for example, if you see this picture, you can see that, for instance, there is factors of like the wall color, the floor color, the object color. So for example, if this room is our world, and we want to learn one concept that is a wall, for example, if we paint the wall to another color, like, I don't know, like red, for example, you will understand that this is still a room. It will be like the same. You just change like some factor of variation. So in the same way, the representation should be robust enough to like learn the concepts, to learn these factors that are underlying in the data. But why this is important? Well, first of all, like data efficiency, you want to have representation that can be like generalized to other tasks. So you don't need, for example, to learn everything from scratch. You can have a representation that will be useful for many tasks. Also, you can manipulate the latent, which is basically you can, for example, you can see here in this picture that, for example, the wall probably in your data set, you don't have like a yellow wall. Maybe you have like this cube, the cube is yellow. But because the model understood what is the color yellow, could extrapolate to other concepts. That is why it's like important to have this concept grounded in our data representations. Just at the end, basically, learning disentangled representations means to learn the structure of the world, basically of our data. Now I want to talk about like a little bit about mutual information decomposition. Just a little brief introduction about this information theories. You should like remember about entropy, which measures the uncertainty about a specific variable. A mutual information, which basically as well measure what kind of information a variable told me about another one. In this case, like the information about X that told me about Y. And the good thing about the mutual information is that this could be expressed as a KL divergence, which is will be in the next minutes why this is useful. My research first takes some inspiration with information theory and neuroscience. First, in the information theory approach, we should know that the mutual information could be decomposed in several components. In this case, could be unique, redundant, and synergistic mutual information, which basically you could see here in this diagram. That is quite easy to see that the yellow part is the redundant, the blue part, it will be like the unique information, and the light blue part will be the synergistic information. So, but with 2 variables, it's quite easy to see, but with 3 variables, it's quite hard. And imagine that these variables will represent later our latent representation. So we can imagine that we can have at least 10 dimensions in our latents, which could be like quite hard because it will be exponential increasing. So it will be quite hard to compute. In fact, computing the synergistic, the redundant, and the unique mutual information is still a topic of research. So what I want to do now is just give you a little bit intuition about what is synergy. Synergy, or the synergistic mutual information, is easy to understand from the canonical example, which is the XOR gate, that basically tell us that we need 2 variables in order to express one output. In this case, we need x1 and x2 to express y. Why is this like it's not desirable for the task of disentanglement? because we said before that we need to get some information independence in the latent space. So we don't want that, for example, that the wall and the lighting have some correlation. We need to be able to play around the concept of wall, could be like extrapolate that without, like, for example, moving the lighting. So that means that if we want to like paint all the wall, that doesn't need to affect how the floor is, like the shape of the floor, or how many chairs are, or like the lighting in general. It should be independent. So in order to compute the synergy, we have like different metrics. I'm just going to talk about, I think, the most suitable one for our for this presentation, which is the IMAX synergy. The intuition here is basically the synergy is, we see here is the light blue part, right? So all this circle will be the mutual information. And if we want the light blue part, we need to kind of subtract the yellow and the blue part. So this is the same intuition. You can see here the I, this part, the mutual information between X and Y will be the big circle, minus this part will be the rest of the circle, which is not, in this case, will be the yellow and the blue part. So in this way, we are kind of computing the synergy mutual information. And this is important because this kind of formulation is easy to compute using the KL divergence. This is other metrics, are quite similar, different approaches, but the main thing about these two other metrics is that we here can see that there is like a bound between all those metrics. And if we see here that our estimate is an overestimate, so that will be useful to know in the next slides, because the thing is this is an overestimate will be useful for our formulation. The other approach from neuroscience, which basically says that our neurons encode the information from the stimulus of the world, and in the way of these little blocks that is called spike trains. So what is the intuition here? Is that if this representation, if this encoding that we have in our neurons convey more information together than separate, we could say that we have synergistic information. But if they are like independent of each other, we will say that we have some kind of information independence. So neuroscience and information theory both try to develop some intuition about synergy. So about the model. The model first, there is some work before to the task of disentanglement. The beta VAE is quite popular right now. The factor VAE as well. They are both quite state-of-the-art models. The InfoGAN as well it's a different approach using GANs. Still, it tried to maximize the mutual information. So the intuition in our model basically is that we know that synergy is not desirable for disentanglement, as we mentioned before. So we want that the latents be as informative as possible. So in that way, we want to minimize synergy. So these have the basically VAE formulation, which start with the elbow here, and this will be like the next, that's basically the synergistic part. If we try to transform all this formulation from the KL and play around with a little bit of maths, basically, we could try to have this nice last formulation, which is this one, which at the end is basically the elbow minus the synergy. But we can see here that this AW will correspond to the worst indices of the latents. So the intuition here is we are going to optimize the VAE in the same way, but we are going to penalize the worst indices of the latents. So if my latent representation from 1 to 10, the indices that are really important for my representations are like, for example, 1, 2, and 3, it will penalize the rest, the complement of that. During the training, we basically are using the same architecture as factor VAE. We are not modifying the architecture at all, and we're going to train it in a two-step optimization when we first train the elbow part, and the next part will be corresponding to the synergy part. For the experiments, we are using the benchmark, which is basically the DSprites dataset. I want to explain a little bit about this. The image on the left, we could see here the latent traversals. This means that for each of the columns we see here, we are traversing the latent from -3 to +3 standard deviations. So basically, we could see here that these dimensions, for example, the dimension 6 correspond to a scale. The dimension 3 and 8 will correspond to rotation. In the image on the right, we could see also it is called the mean activations. And it's really visual because we can see here that, for example, rotation is quite nice. You can see here clearly in rotation and scale that it is aligned with the generative factor of variation. The same with y-axis and with x-axis. Here we could see, for example, it's important to see that these two are kind of state-of-the-art models right now, but this is the plain VAE. And you could see here in this part, which is quite, I think, intuitive to know that every single latent dimension explains a little bit has a little bit of information about each generative factor. So in order to explain like position or scale or rotation, we will need many latents, and we don't want that. We want that to be that each latent will be informative, independent. In comparison with factor VAE, we noticed that factor VAE implicitly also minimize the synergy. Factor VAE, what is basically disentangling by minimizing the total correlation, which is a nice information theory metric, which basically says that it measures the correlation between the latents. So they are trying to get that kind of independence in the latent by penalizing the dependencies. We could see here in the SLFA like the same distribution, basically have different factors of variation as well. And also, I think this is like one of the best examples in the chairs. You could see here in the chairs that each generative factor, each explanatory factor of variation, for example, wheels, you could see here in this example that is traversing from one chair that doesn't have wheels to one that it does. And what is important here is that, for example, for this chair, for this sample of the latent distribution, this specific sample doesn't have any kind of wheels on the data set. But you could extrapolate, you can play with the latents and basically have this kind of framework. And our conclusion is that basically disentangled representations in this unsupervised setting is definitely useful towards like a general artificial intelligence because it will allow us to generalize better. So we should keep pursuing, like in grabbing inspiration from neuroscience and information theory to try to build better models the way, humans basically learn. Thank you.
Yeah, thank you so much, Gonzalo. I hadn't forgotten about Brazil. How many people we have from Brazil? There you go. Yeah, next presenter is actually from Brazil. Guilherme, how do you say it? Guilherme Resende Borges. He's a master's student in computer science at Universidade Federal de Minas Gerais, Brazil. Also one of the top 10 universities in Latin America. Apart from his work there, Guilherme has been in IIT in Chicago as an undergraduate researcher, and he's gonna present an evaluation framework for Granger matrix extraction via point processes. Thank you, Guilherme.
So how do I? This one? Hello, good afternoon. My name is Guilherme. I'm a master student from UFMG, and I'm going to present an evaluation framework for Granger matrix extraction via point processes. So let's say you have 3 users in a social network, and when Blue posts something on his social network, Green tends to post something right after that, and vice versa. And the same thing happens when Blue posts something, Red also tends to post something, but the inverse is not true. So we want to estimate these causal relationships. We call them Granger causal relationships, but we don't actually observe them. What we observe is for each user a sequence of timestamp events. So this sequence can be, for example, posts on this social network. We call each of these sequence a point process. So a point process is, as I said, data containing events occurring randomly in time. They have been used to model occurrence of earthquakes and aftershocks. So you want to know, for example, if an earthquake happens, how it influences other aftershocks. Same thing for spiking neurons. So if a neuron spikes, what other neurons will tend to spike as well, and as I have mentioned, activity in online social networks. So a point process for each of these, for each of these nodes can be completely characterized by this conditional intensity function, this lambda t. This is a function over time that can be interpreted as the instantaneous probability of an event firing at each time. So a process with the same conditional intensity function can have many different realizations, but you would expect that most of these events on these realizations are concentrated in regions where the function has higher values. So in our work, we analyze multivariate point process. These usually have a form like this. We have two main factors. The first one is the baseline or exogenous intensity. There's an error there, sorry. This is a constant rate that would be the rate of exogenous events occurring. And the second factor is a sum over all the processes of the network. This sum can be over the entire history of all events of all the processes. This is what we call a Hawk's process, but there are other variations as well. There is a kernel function that is calculated with the current time and the past time of each past event on the history of the process, and it establishes how the influence on the conditional intensity function decays over time. And there's also an alpha parameter that is what we're interested in for estimating those causal relationships. The alpha captures the influence of a process B on A. So there have been several different methods proposed to estimate these causal relationships. However, they mostly employ a different evaluation methodology. So there is a variety of metrics, and most of them only use a few of them on a few data sets, which makes it hard to compare the newly proposed methods or even the established methods within themselves. In this work, we have analyzed 7 models to which open source implementations are available. These, the references are at the end of the talk. These first 6 models are based on Hawk's processes, which analyze the entire history of all the process, and the last one uses a different kind of process, a old process, which only looks at the last event for each process to infer the parameters. So these methods all have varying complexities. Here, N is the number of events, and K is the number of processes. So this is the complexity per iteration, and we run the algorithms until convergence. Most of them have complexity, cubic complexity, either on the number of events or on the number of processes. The two most recent ones and faster ones is Granger-Busca, which has a smaller complexity because it uses, as I said, word processes which have a simpler form of the intensity function, and NPHC, which only depends on the number of processes. So to try to create a common framework for evaluation of all these different methods, we have used some metrics that have been previously used and also devised a new set of metrics. They can be roughly grouped into three categories. The first one, we compare the estimated influence matrix with a ground truth matrix that's dependent on the data set. And we also use simulation of events. So if a method estimates the parameters of a point process, we can use them to simulate many series of different events and then compare them with the real series. These, we compare them regarding the number of events generated and also the distribution of inter-event times. So to illustrate, as I have said, this is a table of metrics used on the evaluation of each of the methods on the proposed papers. And as you can see, most methods have only been evaluated using 2 or 3 metrics, and there is no metric used for all of them. So we consider that a common framework is necessary for comparison between the methods. So also some metrics are not always suitable for the task. For example, one of the most commonly used is the rank correlation, which is the Kendall-Tal rank correlation for each row of the matrix. So what you do is rank the top influences of a certain node and compare these rank with the ground truth rank of the network. However, since the matrices we work are typically sparse, these rank will be often dominated by ties, by values that are 0, or by values that are very close to 0. So the rank difference might not be very significant. Similarly, another commonly used metric is the relative error, which might also not work for sparse matrices, since there is a division by the value of the cell, and in sparse matrices, this will be close to 0 or equal to 0, so some overestimation can throw the metric into weird ways. So the first data set we analyzed so far is the meme tracker data set. This is a blog data set which we have the posting times of each post on blogs, and we also use the hyperlinks between one blog to the other to encode the influence. So in this table, I have only run the metrics that compare the estimated matrix with the ground truth matrix. The methods are ordered by the top are the best ones, and on the bottom are the worst ones. And under the parenthesis is the value of each metric. So in this data set, the Granger-Busca method did well on all 3 of them, but we expect that no method will dominate when we consider the other metrics as well. So besides the meme tracker data set, we also have tested on few simulated data sets. So this is a simulated data set using a Granger process. The only one of these methods that actually tries to capture a Granger process is the Granger-Busca. So you would expect it to do better, but still it doesn't dominate on all metrics. Some of the other methods based on Hawk's process also do best on especially metrics, trying to evaluate the number of events generated in a simulated process. This is an illustration of the matrix we're trying to estimate. The first one on the top left corner is the ground truth, and the other are the estimated matrices. Some of the methods based on Hawk's process do estimate do capture a little bit of the structure of the matrix with some false communities. But some of the other methods based on Hawk's process don't. They can capture any kind of structure at all. We also have tested the methods on a simulated data set with a Hawk's process with an exponential kernels. The HDM4 method is actually made specifically to estimate a Hawk's process with an exponential kernel. But again, it doesn't win on all of the metrics. There is some variation. Particularly, Granger-Busca wins at the precision at 3, which means it's best at capturing the top influences on each node, even if it's not based on Hawk's process and we're simulating a Hawk's process. Here is the matrix. Again, the ground truth is on top left. And in this case, most methods do better since they are all based on Hawk's process, except the last one. But still, there's no perfect method. We couldn't find them all. And this is still ongoing work. We want to refine the set of metrics, the framework, and also analyze the statistical significance of each metric. Some metrics might not be suitable for the text, or might not be suitable under certain data sets. As I have said, sparse matrices pose problems when using a lot of these metrics that have been commonly employed in past works. That's the end of my talk. Thank you.
Thank you, Guillermo. Well, next we have Jorge Luis Guevara Diaz. Jorge is a researcher at IBM in Sao Paulo in Brazil. He actively performs research in artificial intelligence for solving and giving smart data-driven solutions to problems arisen from oil and gas companies, and for applying machine learning and data science solutions on the natural resources area. He holds a PhD, an MSc, and a BSc in computer science. And Jorge will talk today about support fuzzy set machines, from kernels on fuzzy sets to machine learning applications. Thank you, Jorge.
Thank you very much.
Applause for Jorge, please.
Okay. First of all, thank you to all the organizers for this nice space to bring all the Latin American people here and to meet each other. That's really nice. Okay, my name is Jorge Guevara. I'm from IBM Research, and this is a joint work with Roberto Irata from the University of Sao Paulo, Brazil, and Stefano Cagnou from the University of Normandy, France. Sorry for the slides. Actually, I was working on a smaller set of slides, but I was having some problem to uploading and to updating these slides into the server. Then I'm going to skip a lot of them. Okay, but basically, what I'm talking about, what I'm talking to right now is talking about the kernel machines and kernel fuzzy sets, and to define what is a support fuzzy set machine. Okay. Basically, in machine learning, we have data, like a set of images, we have data frames, we have graphs, and we wanted to solve some tasks like classification, regression, density estimation, or clustering, stuff like that. But at the end of the day, we wanted to estimate this functional relationship using the data and using some methodology. For example, you can use deep learning, you can use decision trees, you can use kernel methods in order to estimate this function. And also, we work with several data representations, like, for example, you can represent an image as a vector, or using some kind of distribution like a conditional random field, or you can, for example, if you can work with some uncertainties, you can model uncertainties using some probability measures or fuzzy sets, something like that. But at the core of these procedures is a similarity function, a similarity measure. Basically, a similarity measure is a real valued function that quantifies the similarity between two objects. You have a lot of them. For example, the inner products is a similarity function. Okay, you have the cosine similarity, something like that. The kernel methods is my area of research. Basically, you have that the kernel methods follows this methodology. You have here the data set. You have this kernel function, and with this kernel function, you estimate this matrix here, this kernel matrix. The data size of this kernel matrix is a function of the number of observations that you have in the data. For example, if you have 10 observations, your matrix will be 10 per 10. If you have 100 observations, you will have 100 by 100 kernel matrix. You have a very big data set, okay, kernel, you have some tricks. You can perform some kind of approximation of this kernel matrix to deal with a very large data set. Then you have this algorithm here that uses this kernel matrix, okay? And the output of this algorithm always is a function like this form. It's a function that is a linear combination of the kernel with these values, these alpha values, okay? Then the only thing that you wanted to estimate or optimize here is to find out these alpha values, because actually the kernel function, you know the kernel function, you have the training data points, and you have this test data point. For example, the supervector machines, I'm not going to go into details, but actually you do try to solve this problem and try to estimate these alpha values. Once you have these alpha values, you put the alpha values in this solution here, and you can estimate the hyperplane of the supervector machine. Okay, I'm going to skip this slide, sorry. Also, for example, for the kernel PCA, you have to solve this problem here. You estimate these alpha values because you are interested in computing these agent functions. And these agent functions, basically, if you look to the it's a linear combination of the alpha values of the kernel, and basically the solution is the same given for this algorithm here. The Gaussian process regression also, for example, you can start from a prior function that follows this Gaussian process distribution. This Gaussian process distribution basically have two parameters. You have the mean functions and this covariate matrix that is given by the kernel, okay? Then you estimate the distribution of this random variable. This random variable basically given the data set that you have, and at this point you can see that the distribution follows, is normal distributed, and this mean value basically is given by the kernel operations, and the standard deviation you can also estimate using these kernel operations. Then basically, if you wanna have the value of the regression function, basically you pick the mean value here, and if you do some mathematics, you can prove that this value basically is the linear combination of these alpha values with these kernel functions. Okay, you have the supervector data description as well. For example, in this case, you wanted to estimate the minimum enclosing ball for using the data that you have, and you wanted to use that model in another test data. If a point lies outside of the minimum enclosing ball, you label that point as an outlier or novelty. Okay, if the alpha values here, if you replace the values in this output, you will estimate the center of the minimum enclosing ball. Of course, you can estimate the radius of this minimum enclosing ball by looking to the dual problem of this dual and analyzing the Lagrangian coefficients of this optimization problem. Here in the kernel 2 sample test, basically you are interested, you have two sample of data points, and you are interested in discovering if the samples comes from the same distribution of two different distributions. Basically, you wanted to test if P is equal to Q. And using, for example, this kind of embeddings, you can embed this probability measure using kernels. Okay, basically you have here a function, and you have this random variable that follows this distribution P, and you estimate this norm in these proper Hilbert spaces. But of course, you have this empirical estimation, okay, using kernels, and as we are going to see in the next slide, you can use, you can prove that these kernels basically are inner products, okay, and you can use these representations here, and actually we will have playing with these functions and these alphas also here, okay? And also the radial basis function neural network. You can, for example, estimate some prototypes using clustering here, and but at the end of the day, you wanted to estimate this W, and actually this exponential function is a kernel, okay? Then, all these methods basically share this nice thing, okay, this workflow, and they have this represented theorem that basically say that they try to optimize this objective function with some regularization here, and the optimal function basically will be given by the linear combination of these alpha values and the kernel, and this training and data points. That is very nice, okay? That is a very nice step that is shared for all the kernel methods, okay? If you look to the kernel matrix, basically the kernel matrix is a similarity matrix. For example, we have points, we have a data set with 2 classes here. If you plot the similarity matrix, you can, for example, look here that we have 2 different classes. But there is a kernel parameter. For example, if you put some parameter here, no point is similar to each other, but here every point is similar to each other, then you have to optimize this parameter using cross-validation, for example. And the kernel basically defines a reproducing kernel Hilbert space. A reproducing kernel Hilbert space is a proper Hilbert space of function that basically you have. The beauty of this is that you have here a data set without a mathematical structure. For example, the only thing that is required is for this data set is to be a non-empty data set. But using the kernel, basically you transform all the values to functions. You have here a vectorial space. You can perform some kind of projection, inner product, something like that. Then basically the main ingredient for this for the construction of the reproducing kernel Hilbert space is the kernel, okay? This is the difficult part, because if you have a function and if you wanted to use this function as a kernel, you have to prove that for every natural number, for every combination of real numbers, and for every combination of points, not in your data set, but the points of the input space where your data set lives, you have to prove that this is always greater than 0, and that is very complicated, okay? But if you prove that, you can say that for every point here, there is a function in the producing Hilbert space, the representative function of this point here, and if you pick a point here, and if you pick a function that lives in this space, and you perform the inner product, that is equal to the evaluation of the function at this point. Using this, we can have this nice property. If we pick 2 points in the input space, and if we estimate the kernel, basically this is an inner product of 2 functions, and these functions basically are could be infinite. You could think that infinite dimensional feature vectors, for example. Okay, I'm going to skip this thing here. But for example, here, this kernel, the exponential kernel, you can prove that basically is the inner product of 2 infinite dimensional vectors, okay? Okay, you have another kind of kernels, for example, the kernel between probability measures, and you can use this kernel base and some empirical estimation, but actually this kernel is very nice because the space of the probability measures is not a vectorial space, but using this kernel trick, you can induce a topology in this space. The implementation is very simple. You can loop over these 2 summations and use a kernel base and 2 sets in order to estimate this kernel here. Okay, I'm going to skip this. This kernel, actually, that looks very ugly, is a kernel that I use a lot in my work, because I work a lot with geostatistics, and it is a kernel that geostatisticians use a lot for making this kriging procedure, trying to estimate. It's like it's a regression, okay? It's a regression thing that they try to estimate unknown points based in the data sample that they have. Okay, we have a lot of kernels. And some properties, the kernel is a covariance function, it's a similarity measure, are related to the metrics. And basically, you can define the kernels on no empty set, and you can use the kernels on no vectorial data. Okay. The kernel of fuzzy sets. Okay, we have a lot of papers on this issue. I'm going to put some basic results of the kernel of fuzzy sets. And the main motivation basically is the subjective uncertainty, because not all the uncertainty you can quantify. For example, we have it's a very common problem, for example, for the geologists to pick some signals from the wells, and he tries to label and to put some labels. Once he puts the label, he assigns a number of confidence. It's not a probability number. It's basically a confidence number based on his expertise or based on other factors. For example, we can think that we have this observation and this confidence value here, but also we can have some confidence values and this on each value here. And on the extreme case, instead of having numbers, we will have functions instead of values. For example, we could think that we can define this 0, 1 valued function in each attribute. This is a fuzzy set, okay? The main idea is to incorporate this kind of data in the kernel methods in some way, okay? I'm going to skip that. This is a kernel, okay? We construct this kernel between two fuzzy sets. This kernel is defined by the tensorial product of these two kernels, and using the data and the uncertainty values that we have, and we prove that this kernel is positive definite. The nice thing is that, for example, the space of all the fuzzy sets is not a vectorial space, but actually you can induce a metric, and you can have this nice geometric interpretation using these kind of embeddings. Okay. Actually, that kernel is a class of kernel. It's not only a kernel. You can generate a lot of kernels from this definition, okay? From this definition here. Okay, for example, we have 4 examples of kernel of fuzzy sets. Okay, more examples. Some properties, basically, that we can mix the two interpretations for uncertainty. For example, we can mix fuzziness and randomness using this kernel. We prove that this kernel actually embeds empirical probability distributions in these spaces. Okay, and actually we make some experiments and we prove that these classifiers are noise resistant. Okay, okay. Another kernel, I'm going to skip this mathematics here, is this kernel here. This kernel, for the derivation of this kernel, we use fuzzy mathematics. The basic idea here is to estimate the intersection between two fuzzy sets, but keeping this kernel positive definite. That is, this kernel actually could be represented as the inner product of the embeddings of these two fuzzy sets in a reproducing kernel Hilbert space. Okay. Also, this is a class of kernels. We can derive here a lot of kernels based on that idea. Okay, we have here this another kernel, okay, the non-singleton kernel of fuzzy set. Basically, this kernel is also based on fuzzy mathematics. This kernel, basically, we find out this kernel by looking some classic fuzzy systems, and we realize that actually this kind of mathematics in the fuzzy set community knows. Uses a lot, basically defines a positive definite kernel on fuzzy sets. Okay, also this kernel defines a class of functions. You can generate several kernels based on that. For example, you have this observation, and this observation, basically you have functions instead of numbers, and you can compare these tuples, the x and y of observation, using this kind of function, where you are representing each function here by this fuzzy membership function. Okay, basically it's a Gaussian function over each value here. Okay, okay, we have several kernels here. I think that this material is going to share it about all the presenters here. If you have more questions, or if you are interested in the details of this work, you can contact me. Thank you very much.
Okay. Thank you so much, Jorge. I'm sure people have questions. So much mathematical knowledge there. So next, we have another Jorge. Jorge Gustavo Madrid Perez. He's a software engineer who's currently a master's student in computer science. at the National Institute of Astrophysics, Optics, and Electronics, which is in Tonantzintla, Puebla, Mexico. Isn't that a beautiful name? In a way, it's a well-renowned astrophysics institution where some of the younger talents in Mexico pursue their research career. And Jorge's research interests include meta-learning and automated machine learning, AutoML. And his presentation is actually towards AutoML in the presence of drift. Thank you, Jorge.
Well, thanks to all the organizers and sponsors to giving us the opportunity to present our work here. And also thank you to all of those who showed interest in our poster. There is the reference of the full paper. I'll start talking about where I come from, which I'm proud. It's the INAOE, the National Institute of Astrophysics, Optics, and Electronics. I think I can objectively say that this is one of the best research centers in Mexico if we look at the numbers. It's based on Tonantzintla, Puebla, which is near Mexico City, as you can see in the map. So I'll start defining two of the concepts in the title of this work. First, the AutoML, or automated machine learning. We traditionally work in machine learning in this setting. We have, firstly, a huge amount of data, and what we try is to solve a problem with that data. And what we usually do is an expert, like the ones are here, tries to find a model that solves the problem. So we have to select a pre-processing method, select a classifier, whether it's a supervised or unsupervised task, and then tune the hyperparameters of that model. And what AutoML aims to is to eliminate the human expert from that equation. The idea here is that non-experts in machine learning can use our technological and scientific advances. You can see this as a black box where you input the raw data and get the full model. The other concept is concept drift, which refers to the changes in data distribution through time. In many real-world applications, we can see this kind of behavior. I listed here some examples: so online advertising, recommendation system, spam filtering, econometrics. Of course, there are some solutions already to this kind of problem, but what we are aiming here is different, is taking the human out of this process, making it autonomously to deal with this kind of data. So that is what we refer with AutoML in the presence of drift. And this was inspired by a challenge that took place here at NeurIPS. And we did the first approach to it, and this is the setting for the challenge. So first we receive training data, structured data with labels to make our first our first model, let's say, and then we will continue receiving data through time, but we cannot change our code later. So our method has to autonomously change the method it produced, the model it produced to adjust through the changes in the data distribution over the time. We don't know how it is going to change the data. So that's part of the challenge. So we also receive the data in batches. So let's say we first receive a batch of data for the testing part. We have to make evaluations with our original model there, and then the labels for that batch are released, and we make evaluations there. Then we receive another batch of data, and the same process is made, and so on. And in the end, for this challenge, the average of the evaluations for each batch is made. And well, as I said, this was a first approach to that setting, and this is our proposal. We decided to extend AutoScaLearn, which is a state-of-the-art solution in AutoML. It has won the previous challenge in AutoML. It is based on scikit-learn, which is a standard library used in machine learning. It's also robust and open source. So I'll briefly describe how AutoScaLearn works. First, it has a meta-learning phase where they learn from previous tasks. They take data from OpenML. And then what they do is they calculate some meta features from those tasks. And when they receive a new data for a new task, they see from which of those tasks is more similar to the new one. Then with that information, they reduce the search space, and the Bayesian optimization method is performed to select the preprocessing, feature preprocessor, and classifiers. They select the top classifiers, and then they build and assemble from those. Now it's important to say that it is an ensemble because our proposal bases on that. So this is the proposed extension. It is very intuitive. So we receive the first batch. We train using AutoScaLearn, and then for each batch of the test data, we check with a state-of-the-art drift detector if drift is happening in the data. So if we detect that the drift is happening, we adapt the model. We reset the drift, and if there is no drift, then, well, we don't do anything. We go to the next batch. So for detecting the drift, we use this method. It's a FHDDM, which is based on the Hovding's inequality. What we have to take into account here is that it uses a window, and this window slides through time. So its size is fixed, and what we send to this window is how many examples did it get wrong. If it accumulates enough evidence that our current model is not working well, then, well, drift is detected, so we have to change something. And the mechanisms we chose to do that adaptation are these. We tested 4 different mechanisms. We divided them in 2 strategies. The first one is a model replacement. So we simply train again using all the data from, okay. We train again using all the data available. The other strategy we followed was trying to change something from what we have from the ensemble that AutoScaLearn produces. So the first approach was trying to update the weights with the most recent data, using all the data available, or trying to train a new classifier and add it to the ensemble. So here are the results. We tested it in 2 kinds of data sets. The first one is a benchmark data sets for concept drift research. Most of those are synthetic data. And the second kind of data we use was the data for the AutoML2 challenge. I cannot talk much about this data, but we know for sure that there is presence of drift in this data. I included here two interesting results from the benchmark data sets. In the first one, we can see that, well, in both of them, we can see that replacing the whole model works best. But for example, in this green line, we can see that if we forget everything and we just take the latest batch of data, that may be counterproductive to our model. Instead of making it better, it makes it worse. So it might not be a good idea to forget everything always. And here is another example that I think is interesting. Here the drift is very abrupt and it's completely the opposite. So the classes that were positive becomes negative and vice versa. So most of the methods we produced failed. But this is a strange case if we want to work in real applications, in real world applications. So those are the results for the benchmark data. As we can see, and as we could expect, the replacement of the full model works best most of the time. In AutoML, usually we rank the methods, and well, this was clearly the best option. Sorry. But the interesting results we got were from the AutoML 2 challenge. Here, this is data from a real-world application. And here, the replacement of the full model is not always the best solution. Sometimes even just taking the latest batch looks like the best option. And by the way, the previous results here are accuracy, but here we are reporting the same metric that was used for the previous challenge, which is 2 times the area under the curve minus 1. So what we learned from these intuitive mechanisms is that, well, first of all, we got promising results, but also that there are different types of drifts, and it's not easy to determine what is the best adaptation mechanism for each task. It really depends on it. So how could we scale these mechanisms to work with millions of samples? That was also one of the challenges of the most recent challenge. Well, but we only tested it with the data from previous challenges, but it was a first approach, and we did this before the challenge was open. But now the results of that challenge, the AutoML 3 challenge, were released today. So it would be interesting to see what the other methods did. Thank you.
Thank you so much, Jorge. So we have like 10 minutes for a quick coffee break, so you can also go to the bathroom, etc. Just after the break, we have a senior member of the IEEE, or IECubo. And then later, we also have 2 people from MIT, so you don't want to miss this. It's going until 6. I know it's been a long week, but please stay with us. Thank you. Yeah, I think we turn off the lights because on the back, they turn off the lights because on the back we couldn't read.
Yeah, that's me.
There you go.
It's beautiful.
Yeah, I think with the light off it's better. Were you on the back?
I was on the side.
Oh, I mean, was it better with the light off, or what do you think? Okay.
One thing is, I'm not sure if the camera guy is happy.
I know, because it's streaming.
I think he's recording the first. I don't know, but if he's recording the first
I'll
one,
ask.
it might be.
Yeah, the person is just gonna be. I think the content is the important part. Yeah, they're streaming. I guess maybe there's some people.
Oh, is this a timer?
Yeah, well, they'll let you know. There's like a guy there is saying 5 minutes, 4 minutes, but yeah, 3:30 will start.
Cool.
I'm gonna go to the bathroom.
Yeah. Well, there's no exit.
Yeah.
copio y lo guardo. Y en mi tiempo libre estoy viendo.
Nice.
¿no?
Me preguntaba... Vamos a probar porque... Dame un segundo.
Sí. Todas las cosas que no entiendo lo pongo ahí. Con el tiempo se va metiendo en la cabeza. Está el Word, por ejemplo.
¿Qué es lo que quieres probar? Ok. Ah, o sea, dejarlo abierto, dices. ¿Chrome te sirve? ¿Podemos abrir Chrome para... Él luego tiene que hacer una demo?
No, dale. ¿Tienes el link? Ok.
Para dejarlo preparado.
Sí, pues escríbelo.
Sí, ¿quieres que escriba? Sí, déjalo preparado y luego lo... Uy, perdón. Como no, nadie va a abrir Chrome.
Mucha suerte, ¿no? Gusto verte con.
Ya está.
Muy contento con los
Perfecto.
logros.
Dejamos
Ya
ahí.
está.
Este es el tuyo, ¿verdad, Pablo? Este es el tuyo, ¿no? El tip.
Sí.
Perfecto. Okay, so we're going to start again with the session. Just a reminder, we still have 9 talks. Next one, we have Pablo Rivas. Pablo, he's a computer scientist, a deep learning evangelist. He's a professional member of the ACM and a senior member of the IEEE. His degrees are in computer science, electrical engineering, and electrical and computer engineering, his PhD, from the University of Texas, El Paso. Currently, he's an assistant professor of computer science at Marist College. Before that, he was a postdoc at Baylor University and a NASA intern. He's going to present a deep learning approach to sign language recognition using stacked sparse autoencoders. Thanks for being with us today, Pablo.
Thank you. It's nice to be introduced and someone who can correctly pronounce my name for a change. Rivas, that's good. What I'm going to talk about today is a project that I've been working with some people from Nogales Institute of Technology. One of them, Ezequiel, is my brother, my little brother. So this is his master's thesis in a way, and the other people are our colleagues who are also directing the work, and my grad student, Deep, on the far right. When I was little, I was investigating how people can communicate in the Olympics, asking questions to my dad, like, Dad, what are they doing? Why are they doing it so fast? And I was very intrigued at a small age about how they're doing this and how I wasn't able to understand anything that was going on. And so we have this problem of the American Sign Language and how it's how people can communicate through it. There is usually how people communicate is that they learn to use sign language so that they can so that we can communicate with people with a disability. It is usually a more challenging task on the person with a disability to communicate with us. So really, they're making a greater effort. So this is another example of how a minority has to do an additional effort to being able to have equal access to communication or human interaction in this case. Because I don't see human beings learning, or we are not taught to do this sign language for our benefit. And I'm grateful for, if you remember seeing a strategy booth down there in the demonstrations, they have a challenge of how to do hand gesture recognition. So I appreciate that because it's a difficult thing to do. So in our efforts to model or find ways to provide technology to do this, the work was to model the American Sign Language. We are excluding from the alphabet that is on the screen some letters that require motion. So we're looking at static pictures, and we're excluding J, for example, that goes like this, and Z, that goes like this. And we're also joining two letters that are similar, like number 2 and V. And we're also joining W and number 3. And so the data set it's open source. We obtain this open source. You can access the GitHub, you look at the references. And it's using Kinect as depth camera. So there's a segmentation process that is going on, and you get the images in this form after they've been segmented. So in the example, we have number 1. It includes rotations and changes in angle as well. And the number 2. So these are examples of how that is. When you try to visualize the data in the 31 classes, that includes all the numbers and the letters, using PCA, it's clear there is not a trivial classification problem. And if you look at the TISNA visualization, you can see in the close to the center, there's a big overlap of classes in some groups, while others are sort of easy to classify. The existing approaches are shown on the screen, and the most recent one that was done in 2015 that uses convolutional networks and are the authors of this data set. They report having 99.9% of accuracy when they split the data in 50, 25, and 25% for training, testing, and validation. However, the problem is that the authors, or some of these good examples, are using very complex and complicated convolutional networks. And so one of the points that we're trying to do when replicating this research is why convolutional neural networks all the time? I'm kind of getting sick of it. I'm just kidding. I'm not sick of it. But it's a lot of CNNs for this, CNNs for that. Can we do this in a simpler way? So we started to investigate if it was simpler to do it with autoencoders, for example. This is just the output part of the CNN that the authors are proposing. It's ignoring a bunch of 2 other screens that I would require on the left-hand side to tell you the other layers that were being ignored here. So our point is that if you use an approach of using autoencoders, we claim that it's obviously simpler than CNN to understand and to model. And it's more efficient than CNN when deployed in the assumption that we're using a sparse version of it. And also it's faster to train than CNN for a similar number of layers, of course. And we obtain a similar performance. And we're saying that CNNs are not the solution to every single problem in pattern recognition or computer vision. So if there's something simpler, let's try that first, and then let's go with the big guns. So let's talk about autoencoders for a little bit. The autoencoder is this model or neural model in which we have a number of neurons in an input layer that are learning an encoded version of the input. And there's a second layer associated or paired with it that is reconstructing the input. This process is unsupervised for the most part. Of course, it's supervised in the sense that it has a loss function that it minimizes. But the beauty of it is that it's not trying to learn a specific class, but it's just learning to encode information. So for more about this, look at the videos from Jeff Hinton about deep belief networks and others, and how this enables us to learn more interesting things without biasing a classifier to learn a specific class, just right up front. So autoencoders come in pairs, and so this is one pair. The loss function that we're trying to use in this autoencoder model involves 3 major parts. The first part on the left-hand side is our traditional mean squared error. The second term is a term that involves a parameter theta w that is looking at the weights of the network, and it's trying to estimate how big are these weights, how large are they, and penalize them with a lambda factor. So if you want to have a sparse model, you probably want to penalize larger weights. So sparser models, of course, as you may know, lead to a bunch of zeros in the weights. And if you know about zeros and multiplications, we like those because we don't have to do those multiplications. And so the second part is our traditional KL divergence functions that is measuring how the desired activation of every neuron is deviating from a target. How is diverging from a desired behavior, if you will. And so in these terms, this is the average activation or the average output of a specific neuron. And we have here our traditional linear model that is passed through a sigmoid, or the activation of your choice. So the model put together looks like this. And so 2 pairs of autoencoders is all it took to match the CNN. 2 simple autoencoders. The first one is a downsampling or encoding into 100 neurons, 100 vector of 100, and then the second one is doing 50. Now after this is trained without looking at any classes, and you put the output or you give the target, and you go through the fine-tuning process with the minimizer of your choice, and we're using the loss function E here, which is our traditional cross-entropy loss. Easy, right? That when we look at the results of this, for 5 subjects, the subjects that the authors propose or run their tests with, we achieved an accuracy of 98.8% and a specificity of 99.6, while the authors reported a 99.9 as well. But let's look at what are the mistakes that the autoencoders are making. These are actual number of mistakes out of 31,000 images. So in the left, we have the target class, E, for example, and how many mistakes and which letter was the one that I was confused with. So the first one is an E and an S. You are asking, you may be wondering, what does the E and an S look like? So here's an E, and then the S is that. So as you can tell, if you cannot tell the difference or it's hard for you, it must be a little bit harder as well for a computer to do that. Let's look at, for example, the T and an A. So the T is this, and A is that. So it is A and T, A and T. What else looks, M and N, that's an easy one. So M looks like this. Where is it? Yeah, on the right-hand side, like this. And the N is, you move the finger to the next position. So it's almost identical. So when you move the hand in rotating it, it might be confusing. So when we look closer at exactly which examples are being misclassified, so you look at the input and the predicted outcome. So if the input was this, it predicted that the closest in the space that the autoencoders mapped the image to, the closest one was this. So they look sort of, it's a fist bump, and yeah, I see it, especially when N and T, if you look at these two, they look similar. What I was surprised about is this, A and P. This is telling us something about what happened in the fine-tuning process or the retraining of the network after the unsupervised learning. So if you see that segmentation error below here, it's being confused or matched to the closest pair, which is a P. So this is not good. This is telling us that the autoencoder, well, not the autoencoder, but the network after the fine-tuning is being very sensitive to noise. So in our next efforts, we're inviting our students to investigate into doing an adversarial training as well to reduce the number of errors given that a poor segmentation like this. For those of you who like to visualize the weights, that's what it looks like. The letter that was mostly, or the one that is the worst classified is E, which is the closed fist. If you visualize how the weight or how the samples are being transformed with an autoencoder as you go deep in the layers, that is how it looks like, being the bottom left, the last or the biggest network, and the t-SNE result of that, you can see that we don't have an entanglement of classes anymore. And finally, to conclude, for those of you who benefit of knowing what hardware we're running this, we're using a testbed called Chameleon, the Chameleon Cloud. If you heard of it, this is cool. Try it out. It's open to any institution to try and deploy models on GPUs, and there's CUDA and libraries. We use TensorFlow. We use Python, and so we hope that we have demonstrated that, again, a simple solution like an autoencoder can do as well as a CNN, even though in the complicated situation of having to do a task of classifying hand gestures from the American Sign Language. And so at this point, I would like to conclude and invite you to, if you'd like to look at code, go to my students to get a repo and check it out. Thank you very much.
Thank you so much, Pablo. Next, we have Santiago Pascual from Barcelona. Santiago, he studied his bachelor in audiovisual engineering in Telecom Barcelona, UPC, and MSc also in Telecom Barcelona in 2016, whilst doing research within the Speech Tech for All Spanish project at UPC. He's currently a PhD candidate at TALP UPC in Barcelona. And one of his 2017 papers, Speech Enhancement Generative Adversarial Networks, now has more than 100 citations. Today, he will be presenting real non-volume preserving voice conversion. Thank you, Santiago.
Yeah. Push, please.
Thanks for welcoming me. So today, as mentioned, I'm presenting a system for voice conversion, so I'll first introduce what that task is. Just to mention, my PhD is on speech-to-speech tasks with generative models. I began with GANs 2 years ago, and this is a sort of prototype as a byproduct of my thesis on using normalizing flows, which is a pretty novel technology made by DeepMind 2 years ago, not very exploited, and now generative models come out of this technology. Not to mention that GLOW appeared 2 months ago or so by OpenAI, being a state-of-the-art image generation system following these sort of models. This is more modest, and I'll show you what we can do with it. Voice conversion as a first approach. So, yeah, what is it, voice conversion? As I'm speaking, maybe I could even convert my accentuation, intonation, and identity, but preserving the contents to mimic the speech of some of you. This is voice conversion. So converting whatever I speak to your speech style, but preserving whatever I say. So I could fake as if I was one of you, or I could repair the speech of damaged possibilities for people with pathologies like dysarthria, where they have interrupted speaking style, let's say, or laryngectomy, suffering people who cannot voice because they don't have any more vocal folds. So these are very interesting applications. Typically, this would be a voice conversion pipeline where we would have some training phase and conversion phase in the machine learning world. And in the training phase, we would need some data set for source speakers and target speakers, and we would be basically training some conversion function between acoustic features coming out of both sorts of speakers. And these acoustic features are extracted normally with something called the vocoder, where we have something like MFCC features, something already mentioned in the singing voice detection, very well explained by our colleague before. Using these features in an analysis and parameterization setup, we could basically learn an alignment function between source and target, making this conversion. And during tests, we would just encode whatever is my speech to be converted with acoustic features. Then the conversion would be produced, and we would reverse back that transformation with the inverse parameterization. This is done by something called the vocoder. So out of the speech waveform, I would go frame by frame windowing and extracting some acoustic features. In this work, we use 43-dimensional vectors of acoustic features containing 40 MFCCs, one coefficient estimating the intonation and excitation parameter, which is the pitch, then voiced and voiced flag marking whether I have a voiced or unvoiced speech frame, and another parameter to make this sort of harmonic plus noise vocoder called a vocoder work, basically. But 43 dimensions in the end. Now, what are normalizing? So this is the sort of data we will work with. I'll come into a moment what normalizing flows are, but now that we have these vectors, the way we can train the conversion model is by having either a fully supervised approach or an unsupervised approach. In the supervised approach, which is the easy way, let's say, I would have people saying exactly the same, and I would somehow align the frames such that both speakers would have the same amount of acoustic features. And I would just be training a conversion function like an MLP or a DMM or some statistical model that would convert frames matching in content and just differing in identity, like red to red, blue to blue, etc. Each of these colors means I'm saying the same whether I'm speaker A or speaker B, okay? So I have exactly the same contents, but what about not having the same contents or even differing in languages? What if I have a training set of someone speaking Spanish, another one speaking English? I may still be able to convert the speaking style or the voicing identity if I don't care about the content and I find a way to extract the latent factors of the speech of the speakers. So this is where normalizing flows come into play, because it is an unsupervised way to disentangle the speaker identity information conveyed in the speech, and then we can use it afterwards to make conversion. So now what are normalizing flows? Basically, this technology is about translating, somehow say it like this way, a probability distribution into another one. Those of you who know GANs and variational autoencoders, well, this does more or less the same, but in another approach, and following the maximum likelihood estimation framework. So if I have some probability distribution, P of X, like the green square, the uniform distribution, I'm able to apply some transformation, in this case a linear one, to go to the blue square, so another uniform distribution. And I know that both are probability distributions, they sum up to 1, the density, and the amount of change to go from X to Y has to respect this ratio, which is basically, let's say, the mass of probability that has been moved, the amount of mass, yeah? In terms of logarithm conversion, this is summation, basically. So log P of Y has to be equal to log P of X plus the log of this absolute value of the difference in movement from X to Y. So this in n dimensions becomes the absolute value of the determinant of the Jacobian, which is the transformation matrix, okay? This is important because this allows now us to play with the change of variable rule, which means if I go from a very cumbersome X space to a simpler Y space, I can play with this rule, as you will see, to apply maximum likelihood estimation in the simple space, yeah, not having to compute the acoustic space, but maybe a Gaussian space where we know the maximum likelihood formulation, by just having, and this is quite restrictive, but let's say just having some restriction in the function shape, such that my Jacobian is computable or efficiently computable, and you'll see why. Another important restriction is that my function has to have an inverse. Okay, so f and f minus 1 have to be both in the game. So we have something called bijector, and out of this we build normalizing flows. Normalizing flows is basically a stack of bijectors, and each bijector, as we mentioned, is forward transformation. Its inverse transformation has to exist as well, and a computable inverse log determinant of the Jacobian of this transformation. We will see that out of this verbosity, how do we apply it effectively. But importantly, if the bijector has tunable parameters, we can make something learnable that converts very cumbersome distributions into simpler ones, and vice versa. So this is a slide that we all take from Brizende and Mohamed, the inventors of normalizing flows. And this is basically the shape on which we can apply in each, red square, oh my, okay. In each red square, we apply a normalizing flow such that our very first distribution, a Gaussian one, that's very simple, can end up being a cumbersome thing, yeah? And in the process, we're just applying a function again and again and again. In the end, the log probability distribution of the last cumbersome zk distribution is just the original one minus the summation of volume changes. So this change of variable will allow us to go from this cumbersome thing in the reverse way to the T0 and compute likelihoods there and maximize the likelihood of our data there, okay? Just by having to take into account the volume changes in the way, which is about computing a determinant of a matrix in each step. Of course, this matrix is restricted in shape, and we'll see now how we restrict it in a clever way, following something called real non-volume preserving flow. So I wanted to remark that this was made at the very beginning in 2015 by DeepMind to inject a more powerful prior into a variational autoencoder, such that you can still sample from a simple Gaussian, a univariate Gaussian, but you can make some flow concatenation, and your real prior will be a cumbersome thing. So your VAE will be more powerful in representation terms, but you still sample from the simple thing. And this is differentiable, so it fits very well there. But it evolved so much now in the shape of the functions that now we can make directly generative models out of it. So this is the key component to the generative model we're building, following this Dean et al. Work, real non-volume preserving flows. What is it? It's a clever way to build the functions f and to have an easy computable way of the Jacobian matrix. Why? Because you here see a vector input z and output x. We split it into chunks, let's say. The first chunk, this gray z's, will be just copy and pasted to x. This is a typo, by the way. X from 1 to d is z from 1 to d, I'm sorry. So this is just a copy and paste operation. But that section that's copy and pasted from input to output is also used to compute scaling and shifting factors through cumbersome functions s and m of the other half of the input vector, z. So this other half will be, let's say we split it in half, although it's flexible. The lowercase d is flexible, but in practice we always split by half. So we applied the transformation here like this. And this is also invertible as easily as just applying the, so as we scale here the half of the vector and sum the shift here, we just have to subtract the shift and divide by the scaling. So it's fully invertible. But you may say, what's the Jacobian of this? Well, as we're just copy and pasting half of it, the upper left side of the matrix, the Jacobian matrix, is the identity. So we have diagonal here of 1, so that's it. And it's true that this part is very cumbersome because these functions, it depends on the complexity of S and M. In this case, we can make neural nets. But depending on the complexity, we have very hard derivatives here. But as this upper part here is just zeros, and this down lower right part is the diagonal of the predicted scaling factors in these cumbersome ping functions. The thing is, triangular matrix is just computing the determinant, just the product of the diagonals. So it is completely computable efficiently. So with this clever trick of chunking half of the vector, we obtain an efficiently computable Jacobian, but you may say, okay, half of the vector is never treated, never transformed, right? But we concatenate many flows. But the way in which we can transform everything to become from any z to x or vice versa, from x to z in the end of the flows, We're basically making some permutation and transformation at every of these stages. So this is what was proposed as real non-volume preserving flows. The thing is, how do we use this in voice conversion? Well, we'll get our acoustic frames, each of the vectors we extract from the speech windows, and we will project them with this sort of function I've just mentioned, permutation and two networks, predicting scaling and shifting, and making the real NBP formulation at every flow step. We can apply, for example, 6 flows in our case. And with these simple MLPs, we can get to Zs, to Gaussian space. And we will train there with maximum likelihood. And as I am saying that training with maximum likelihood is maximizing the likelihood of our data, we can make the change of variable, where log P of X will be log P of Z minus the set of Jacobian transformations. So log P of Z will be just the Gaussian likelihood, as easy as that. And now, when I train unsupervisedly all my frame projections and I disentangle them, let's say, into the Z space, how can I perform conversion? Well, quite easily with the concept of saying, I want to estimate where my voice in that Z space, and the voice of any of the candidates to be converted to, so I need a seed of the voice for someone to which I convert my voice, let's say. Well, I will basically project for a recording of a candidate, a target speaker. I will project the frames and compute the mean Z vector. And for me, I will do the same. So I will have the mean of the source and the mean of the target. Our assumption is after averaging enough frames, you remain with the identity because the variability of contents, different contents and different emotions and stuff that you're speaking with are averaged out. So we just apply this sort of linear transformation for every frame of a test utterance I have to convert to the speech of a target speaker. It's just by applying alpha times a director vector of the difference of the mean vectors, the mean of the identity of the target minus the identity of the source. And this, not to mention, this alpha parameter is basically a trade-off to control the distortion versus ID change. So how much am I changing the source ID into a target at the price of having more distortion? So I have some samples. I pre-train a data with the dataset semiotic that has 2 speakers for 1 hour of speech for each of them. And then I just tried a few conversions in between of them. So we can see going from male to female speaker, a bit of the effect. So we go from male to female. Alpha 0 is just the source speaker, of course. It's not even sounding here. Oh.
But I'm glad to see you again.
No.
Lord, but I'm glad to see you again, Phil.
So now if we apply a bit of transformation towards a female.
Lord, but I'm glad to see you again, Phil.
Some distortions appear because of the frame independence modeling, but as we are shifting frame by frame, not modeling transition between them, but still.
Lord, but I'm glad to see you again, Phil.
It becomes more and more female.
Lord, but I'm glad to see you again, Phil.
And in the end, if we go too far, content is even distorted because those dimensions are modified as well. So noise is being amplified to modify the content itself as well. Just as a prototype, fair enough so far. So an unsupervised approach to voice conversion has been used by using normalizing flows. It's the first approach using normalizing flows to this sort of thing. A stack of RMBP-like blocks acts as this density transformation, which is learnable and very effective, as a different approach to GANs or variational autoencoders. And the mean shift operation seems to suffice sort of how to change the identity, although introducing some distortions. So these preliminary results show potential, but we still have to model the transition between frames and also a better transformation that goes beyond just frame shifting. And that's it. Thank you.
Thank you so much, Santiago. So David Uminsky is our next presenter. David, he's the Executive Director of the Data Institute at USF, Associate Professor of Mathematics and Graduate Director for the MS in Data Science program at USF. He was elected in 2015 by the National Academy of Sciences as a Kavli Frontiers of Science Fellow. He's also the founding director of the bachelor's program in data science at University of San Francisco. He holds a PhD in mathematics from Boston University and a BS in mathematics from Harvey Math College. And his oral presentation today is going to be detecting higher order variable interactions, a spectral analysis approach. Thank you, David.
Thank you. I didn't realize I was going to get such a great introduction. Oops. Yes, let me pull you over the side, sorry. Oh, and I also changed the title. So when I submitted this, we actually had some really good results, and then the results got better and more focused, so I figured I'd tell you about those. But before I go too far, there's a couple things I definitely want to say. Please come talk to me afterwards if you're interested in this research, but we're also hiring. We're hiring faculty, tenure-track faculty, postdocs. We'd love grad students, so I will be at the networking session later, so if you're interested in any of that, please come talk to me. So really, this work couldn't have been done with everyone that started in the, with Lillian, Rosa, Sylvia, and Mario. They are pictured right here. And this work was done at MSRI for the MSRI UP program. I was fortunate enough to be selected as the director of research for this summer, and they asked me what topic should we do. It's traditionally a very pure mathematics research experience for undergrads. So I just put the words mathematical in front of the next words data science, and that's what we did. And you also not only see work in this talk based on that work, but you will see a talk by Mario, who's also pictured here, in deep learning that was done there. And the students were actually able to join us, so I'm excited about that. All this was basically done in 6 weeks, which I still can't believe, because it was pretty hard. And basically, we started from scratch on these ideas, because it takes a lot of representation theory, a lot of signal processing, and a lot of domain knowledge in genetics, and I had to learn a lot of that as well. So let's begin. There's basically two words I think that need sort of some understanding. The non-abelian piece of Fourier transforms, so we'll start at Fourier transforms, and then epistasis, which is something I had no idea what it was, and had to learn that. So we're going to do a really, really quick refresher on Fourier transforms. And I want to think of them traditionally first, so the abelian version or the commutative version of them. So here's a typical time series you might see. This is particularly births per day of the year. You look at this and you might think, hey, what should I be asking about this time series? Well, you might want to know a lot of things, but often people want to know things about seasonality, periodicities, and this is, of course, not unique to this particular time series. Fourier transforms are probably the most widely applicable transformation one does on time series data and any data which specifically cares about periodicities and period and seasonality. So what's the idea of a Fourier transform is you have a signal that comes in. It'll look a lot like that. It may not look particularly insightful. You might say, I think I see things in there. And then the Fourier transform says, hold on, let me rewrite that in a new basis. And that basis is the frequency domain, okay? And so it's at its core, it's just linear algebra, right? So you take in this time series data, you say, well, that's an interesting way to represent a signal. I've got a better way to represent this signal. Let's write this as a sum of periodic functions, okay? Typically sines and cosines as we teach, but they can be other things as well. And why is it insightful? Well, instead of replotting them created through those, that series, you just plot the coefficients. And then you look at the coefficients and you see spikes. And those spikes are that piece of information you couldn't see as easily in the time domain, okay? So if there's anything to take away from this idea, that if you create the right basis with the right interpretation, you can get a great deal of insight out of your data, and that's what I want you to see here. So in this particular one, I think what you can see here is actually Doctors particularly schedule things for like Monday or Tuesday of the week, so you see a big spike that's weekly. Then there's like middle of the month versus end of the month. There's maybe some moon effects, and then of course those long periods way out there for New Year's babies and things like that. So as they will describe, the cold months where you stay inside. So that's a way to describe the story of that particular time series by representing it in a periodic basis. But I want to focus a little bit on that periodic basis a little bit more. And as a mathematician, I usually just scribble math formulas all over the talks, but I tried to write this talk with a single formula in it, and that's it. So that is the last, as a PhD mathematician, that is the last formula you're going to see. It's a very simple one. This is basically the arrows that you need that connect these two pieces. So I'll explain it a little bit. The original signal, we probably should have used t. F of x is the original function that came in. And the idea is if you take a basis, which is phi n, and you take the inner product of that function with that basis, you get a coefficient. You take that coefficient, you put it back in front of that function, and then you can reconstruct the signal. Okay? So those spikes are just those inner products. So that piece, let's see, does this work? Yeah. So this piece is what's being plotted right here. Okay, and that n, oops, there we go. That n is literally the n on the x-axis. Okay? All right. I know I'm not supposed to say like any questions, but it's just by nature. Okay, no questions. So again, that's sort of a summary of the Fourier transform as I want you to think about it right now, but there's a new added piece, and that is I'm going to return back to this idea of a periodic function. So that was the insight that took that seasonality period and sort of enhanced features. We'll think about, I think a lot of machine learning practitioners think about Fourier transforms in terms of spectrograms, and those are things you feed into deep learning models, CNN models, because they are a really, it's an enhancement of the signal before you even begin training. But I want to stop for a minute and think about the sines and cosines just one more time, because we're going to have to leave that world, because that world has nothing to do with epistasis and genomics. Well, it might, but not in the context I'm telling you about it. And the idea is sines and cosines are picked because they represent that periodicity, and really they are a continuous representation of a particular group, Z mod NZ. Okay, so if you took abstract algebra, then hopefully you saw one Z mod NZ. Really what it does is there are elements in that group, and as they sort of multiply against each other, they go around a circle. Okay, and that is exactly the group structure that was required to pull out the insight from a time series function. Okay, that group is also commutative or abelian, which makes all of the Fourier transform amazing and easy to use. And often, especially if you come from an engineering background, you sort of never see this sort of discussion right here. But this time it's important. Okay, so I think that's it. Oh yeah, this is just, if you search for Fourier transforms in machine learning, there's an infinite number of choices. I like this one because, again, audio processing, which you just saw a great talk on, but not using spectrograms, I believe. But this is what we're talking about. There's a Fourier transform across the x-axis, and then over time, you actually get these pictures, and these pictures are really great to sort of feed into machine learning algorithms for classification or many other things you want to do. Okay. Epistasis. Now, this was the thing I really didn't understand, but actually became the thing that I wanted to focus on today, because it's one of those moments where, we talk, we've heard a lot of talks today, and a lot of people are attacking really hard problems. Sometimes they're societal problems. Sometimes they are specific machine learning problems. And epistasis is this problem that has essentially sort of ruined the dreams of someone growing up thinking that once the human genome was solved, we would all be healthy again. Or we would have solutions in medicine that would come out of our genome. So that was nice growing up, but it's not true. And one of the major reasons, not the only reason why, once the human genome was sequenced, that we don't have the solutions to all of health, is this problem called epistasis. Okay? So this is an interesting problem. What it really says is a single gene is not likely to contribute to body weight or bone mass density or the color of your hair. It's probably a whole bunch of genes that do this. And that's a really big problem. it's still a big problem. Why is that a big problem? Well, we have millions of genes. And a great deal of computational power is being used right now to detect single mutations to understand particular continuous phenotypic responses like body weight and bone mass. But let's suppose we want to do pairwise. So that's millions choose 2. That is much worse than millions. And now let's do millions choose 3, and you know where this is going. It won't take long before we're bigger than the universe. So if the core problem in genomics, one of the core problems in genomics is multiple genes mutating contribute to a particular issue, we have a problem. In fact, almost an intractable problem. And what I hope to convince you of is this non-abelian Fourier transform might be a really great step in a solution to that direction. And I think it's the first time being used in this particular area. So here's a little bit more biology. This is mostly to remind me what I was looking at. And so to get back to that picture, these are humans. There's 46 chromosomes. There's a lot of ways to zoom in, but you can get all the way down to the base pair sequences. Okay? And those are the things we want to look at for mutations. And genes are a collection of these base pairs. And the idea here is specific chromosomes are often correlated to, wow, that was quick, to particular problems or phenotypic responses. But human data is hard, and there's privacy issues around that, but mice don't care about the privacy. So to attack this particular problem head-on using this Fourier transform, we looked at this well-published result in 2011 about Berlin muscle mice. Just always wanted to say that on camera. And there's 332 of these mice, but particularly what I want you to think is we're going to just study the female mice. You have to do them separately. And again, this pre-processing step got it down to about 164 interesting areas to look at mutations. And if you focus just on chromosome 1, and this is hard to read, but they've identified chromosome B, C, and E as ones contributing to positive body weight. And we decided, let's take a look at that using the non-abelian Fourier transform. So here's the one slide where you have to use non-abelian group theory, and that is to replace the Z mod NZ with the right group structure that will extract out a similar level of insight by writing a new basis. Okay? So what's the new basis and what's the right group structure? That's just the big question for the day. And since we have 5 minutes, I'm going to tell you that it's the symmetric group. And here's the reason why. Think about it. You're staring at N genes, and you want to look at a subset K of those genes that mutate. And you want to be able to study them in such a way that when a spectrum spike occurs, like you saw in the normal Fourier transform, that spike is interpretable and says, that's gene set A, C, and F. And if it's a large spike, you want to say that contributes to positive body weight, for example, which is the one we're looking at right now. And so, again, here's the sort of steps. We've identified 15 mutations, A through 0. We then looked at every single mouse, looked at their gene sequence. So that's a bunch of, the way the data is encoded is 15 columns of genes, a 1 if you mutated, a 0 if you didn't. And the 16th column is the body mass, or the body weight at 70 days. And that's what it looks like. So F is the function that returns the body mass. And then we just computed a Fourier transform. Just as a reminder, this is the time series version of it. And here is the non-abelian transformation of the genetic data. So what you do is you take in this data set, and then you apply a Fourier transform. And once again, you get spikes, and they're broken down in individuals, pairs, triples, 4s, 5s, all the way up to the n over 2 number of mutations. And what you look for are high spikes. And there they are in each of these. And then you zoom in, you say, what is that? Does that actually mean anything? Well, the good news is, like any Fourier transform in the past, you can reconstruct the original signal. And in this case, if that sequence of spikes did not look interpretable, you can reconstruct the signal. And this is the way we've decided to visualize this. This is the entire group of mice. And the ordering on the bottom doesn't matter. There's about 140 of them. And what we've done is painted them blue if they have the particular mutation BDE. Okay, so you just go in and look at the genetic material. We had a very high spike associated to that particular mutation. And We then went in and computed the average body weight for just that set. And sure enough, this detects with statistically significant higher body weight than the previous method. And this is the first time any triple has ever been detected for this particular data set, showing that it's actually more important that all three of them mutate as opposed to any of the individual one does. Even more fun than that is actually we detected that this coalition ABDE, now A was never associated to weight, and it's still not, but as an entire group of 4 mutations, if you make just that subset and compute that average, you actually get an even stronger signal in regard to an epistatic effect. All right, good timing. So to summarize here, pressing the Fourier transform is just as easy for any high or low level set of interactions between genes. And they actually point to the genomics person where to do a statistical test. And that's one of the major problems with the traditional ways to do this is if you take a lot of statistical tests, you're going to be mining p-values. And this signal processing technique says you don't have to do that anymore. You just compute the Fourier transform of the genetic data and then test only the high spikes for significance. And that is a really good shortcut and will keep the power of your statistical tests high. You don't have to worry about Bonferroni corrections or things like that because it's not that many tests. So we're excited about this. And again, there's a 4th order set of mutations. And the Fourier transform says, if you take any subset of those, okay, I guess BDE is it, then I don't know if I detect anything interesting. But if those 4 genes mutate, then I expect a higher body weight mass, and the data supports that. So this is the conclusions to that, which I basically have just said. What's really exciting to me about this is actually a new solution to a really old problem, a really hard problem, a problem that basically a lot of people have given up on. But it's also, you know, more of my interest is in machine learning, and these are just convolutions. This technique where you take a Fourier transform, it's an integration against a kernel. That's a convolution. And so this, if you have things that have group structure or symmetric structures inside your data, and it may be more valuable to first perform a transformation or a change of basis on your data like this before you sort of feed them into machine learning algorithms. And that's sort of some of the next steps we're looking at doing. So the last thing I want to say is I want to thank Laura and the program committee of LatinX and AI. It's a really amazing event. And as I said, I'd love to chat with anyone here that is interested in finding out more about the Data Institute, the University of San Francisco. And this, all this research was funded by these people, and they deserve a lot of thank yous for that. So that's it.
Thank you so much, David. Yeah, thank you so much, David. So next, we have Javier Sánchez Galán, coming from Panama. He's BSc from Universidad Tecnológica de Panamá. He got a full scholarship to pursue postgraduate studies here at McGill University in Montreal. In 2010, he completed his master's in computer science, bioinformatics at the McGill Center for Bioinformatics. He's a PhD in experimental medicine at McGill's Faculty of Medicine, and he now works as a research scientist at the UDP in Panama in the Production Center for Agro-Industrial Research, where he's coordinator of the research group in biotechnology, bioinformatics, and systems synthetic biology. His presentation today is about using deep convolutional networks for the automatic recognition of macroinvertebrate in rivers and affluents in Panama. Thank you, Javier.
Hi, thank you for everybody to be here. I know it's late. I want to be quick. This is a part of a bachelor's thesis, actually, a student of mine. I want to talk about what I've been doing in the topic of detecting images of macroinvertebrates. I will explain a little what it's about. So briefly, in 30 seconds, I come from Universidad de Panamá, which is an engineering school in Panama. Panama is this little green dot that you cannot see, but it's there. And that's the country flag. And probably you know mostly Panama because of the airport, right? Like everybody going south actually have to go to Panama, through Panama. And actually our university is in the main, probably like the left one, the right you see there, but we have campuses in all provinces in Panama. We have, so basically this is part of the project where this is not the main project, basically we are an offshoot of this project, which is called Participatory Biomonitoring of Water Quality with Rural Aqueduct Management Boards. So basically this is the name in Spanish, and the main idea is basically how to explain people how to get water quality measurements in rural settings. So 20% of Panama basically are drinking water from basically aqueducts, like rural aqueducts and rivers. And to be all clear, we don't know the water quality. But one thing it can be done, because is to monitor the microinvertebrates that live around the affluents in the rivers. Usually, in some maybe in developed countries, you have sensors and you have people going every 15 days to measure. That's not the reality in Panama. So this type of bioindicators give us a good sense of the water quality. Basically, if you see some dragonflies and some little snails, that can tell you a lot about the water quality. And obviously, this is happening with the community. So basically, it's I guess a social idea, right? That's how to incorporate, how to teach people to see what they see in the rivers and how to annotate it. Basically, the main the PI of the project came to us and she wanted to do whatever is there described in the first in the top. Basically, she wanted an application that you can actually take pictures of whatever you see in the river affluents, and mark it on a map, on a Google map, right? And send it to a database, which will be at some point revised by an expert in Gorgas Memorial Institute. And then we say, well, you say it's a dragonfly. Well, it's not a dragonfly, or it's a certain type of dragonfly. So the first part, it was developed by another professor in the Faculty of Computer System Engineering. And basically it was this application. As you can see, basically you can map and you can put where it was, and maybe just which one do you see, which one of the little microinvertebrates you see. And basically there are some little insects, and most of the time people get it wrong. Like instead of 6 legs, it does mark as like 7 legs, or I know it's super complex because this because you can able to see it in the water. But we focus on the second part of the problem. Basically, once the images are collected, the idea is to train an expert, basically a machine learning algorithm, to determine if whatever the user said was correct. So main idea was to use TensorFlow and Python, and using on top of Inception version 3, basically just training just the last 3 layers. And as an output will be the classes of macroinvertebrates. One thing I should say, it's for all of you working in biology or medicine, it's very hard to get samples. This is the case in this project because, as you may remember, most institutions have like a collection, but there's only one for each species. There's no 300, right? So the sample set, the image set for us was real small, around between 80 to 150 for species, and basically the student had to search for every catalog in paper or take pictures by himself going to institutions. So it was surprising, but we got interesting results. There was basically 3 methods that we used. Was transfer learning. Well, this is about the database. So basically we did a database which had basically dragonflies, what you can see on the right, and shells, like shells from the little snails will live when they die. For most of the classes, we had to do data augmentation. Interesting enough, it was good for little dragonflies, but with snails, it was really complicated because the symmetry actually does matter. Like where the hole is or where the tip is really, really important to determine the species. And basically, there was four experiments, and basically comparing two types of dragonflies. I will not read the families, subfamilies, but basically two of them, these two you can see in the picture. And the best results, we tried basically the error measurements and kappa, Cohen kappa. And basically we divided in training 80 and 10 for validation and 10 for test. And the resulting was that fine-tuning and data augmentation was the best. The second experiment was the same, but only for 7 classes of dragonflies. The same result, basically fine-tuning with a data augmentation was the best in the 3 data sets. And then we ventured into the shells and actually got similar results, some cases being transferred, just using transfer learning was good. As I said, the symmetry of it changes a lot the results. In some cases, fine-tuning and data augmentation actually give us some better results. And then we tried to do all. So this is basically 14 classes of macroinvertebrates, and we got obviously less results. But instead, in some cases, transfer learning just works. In some cases, fine-tuning with data augmentation works. Also, the student developed basically a TensorFlow app that you can just download and put in your mobile phone and just do like on live, basically. Just the model was trained on the cell phone, and you can use it to have on the spot the detection. Obviously, there were some constraints. The data, for sure. For you, some of you guys working with millions of data sets, just the previous lecture, he was saying about how, one for any test between million choose million. That's not the case here. We have, 150, and I think the class, one of the classes who had the most images was like 300. Very small data sets, maybe it was a long shot to try deep learning, but actually worked. And about the future work is the idea is that not only we have a training model, we have a training model of how to do repeated recognition, but also we want the algorithm learn from the expert. So basically put an expert side by side with the machine and actually have the algorithm learn online from what decision he takes, and he revises it offline, right? Acknowledgement, obviously, Carlos Quintero, my student. He's looking for some opportunities, so just to continue his studies, a great student. And our collaborators, Dr. Fernando Marchand and Dr. Aide Cornejo. This was presented earlier, as I stated. It was the first experiment was presented already in a conference in Panama. And I basically want to thank CENACYT, which is the National Science and Technology Funding Agency. And because I'm part of a Sistema Nacional de Investigadores, so they give us some support. I just wanted to do a kind remark. So happy Mother's Day. In Panama, we celebrate the Mother's Day today. So thank you, Mom, and feliz día, Mamá.
Thank you so much, Javier. We're going to switch a little bit from human sciences into crime. And next we have Mateo Dulce Rubio. He's coming from Colombia. He holds a BSc in Mathematics and Economics and MSc student in Economics from University of Los Andes. He now works as a senior researcher in Quantil Applied Mathematics, a Colombian company dedicated to the development and implementation of math models to solve problems from the public and private sector in Colombia. He actually was the principal developer of a mathematical crime prediction model for the District Security Office of Bogota. And today he's going to talk about predicting criminal behavior with truncated levy flights using real data from Bogota. Thank you so much, Mateo.
Thank you. Thank you all. That was a really nice introduction. Yeah, I'm Mateo. I come from Colombia. I work at Quantil, at this company that develop and implement mathematical models to solve problems from the industry, the public, and the private sector. In particular, we are currently working in the implementation of a mathematical model for the crime prediction in Bogota. This is a work in that sense for predicting criminal behavior with truncated levy flight using real data from Bogota. So in this work, I fit an agent-based model to real burglary data in Bogota, and the estimated parameters validates this repeat and near-repeat victimization and broken windows theory, and without losing predictive accuracy against other state-of-the-art crime prediction models, and shed light on criminal behavior, hotspot dynamics, and efficient segment of police resources. Why bother? Well, crime is a persistent problem in modern cities. Bogota is obviously not the exception, but it is not uniformly distributed through the whole city and constant over time, but present these special temporal clustering patterns. For instance, between 2012 and 2015, just 2% of Bogota's streets were responsible for all the homicides that happened in the city, and those exact same streets accounted for a quarter of all the crimes reported. Well, saying that now sounds obvious. Let's say the police that go there, but in that moment it wasn't obvious. They just received 10% of police time on limited public services. And with this in mind, literature called predictive policing arose to use statistical inference and machine learning techniques to identify these vulnerable crime areas. However, well, these models have a very high crime prediction accuracy. They assume crimes are a random event and attempt to estimate this underlying process of criminal distribution, but fails in giving insights on rational behavior. So I feed this agent-based model to quantify the effect of some mechanisms to the nearby occurrence of crime. These rely on two main mechanisms. The first of all is that burglars often prefer repeat or near-repeat victimization. That is that they prefer to return to previously burglarized places because it's where they already have good information of the types of properties that might be stolen, the routines of the police and their inhabitants. And on the other hand, this broken windows effect that states that the past occurrence of crimes in a certain area creates an atmosphere of lawlessness and crime-tolerant regions that encourages the occurrence of even more crimes in the future. So, for example, this is a histogram of the days that passed when a house is stolen in Bogota, that another house in the same block is stolen again. So you see these spikes, like in the first week. So this was constructed with 10 years data. And whenever a house is stolen in Bogota, it doesn't pass more than a week that the same house or a house in the same block is stolen again. So criminals are actually very happy returning to those places that they already have good information. So the methodology used was proposed in 2008 by Short et al., then extended by Pan et al. Like in 2017. And it is based in the CD represented in a two-dimensional lattice, where each vertex represents a house with some attractiveness level we call A. And this attractiveness level has two components. One is a zero, that is an intrinsic, static component, and this BS that varies with interactions of the house with burglars. In particular, B increments by a factor of theta each time the house is burglarized, and decays with a rate omega, so that this increment in the attractiveness doesn't last forever. And we also measure this broken window effect and near-repeat victimization by allowing the attractiveness to spread, especially to near houses, by a factor of eta, right? So we also model the criminals walking in the city in this grid, following some truncated levy flights. Just think of a random walk, more ugly. And each time intervals, burglars can decide to burglar the house where they are located in their moment or to move to another place. If they commit a burglary, they are removed from the lattice. They go home to enjoy the reward. And we are generating, with the rate gamma, more burglars at each grid vertex. But if a criminal do not perpetrate a crime, he moves to another house following this truncated levy flight with a limited jump range reflecting a limited traveling distance. So the probability that a burglar moves from a house S to a house R is the attractiveness of this destination house AR divided by the distance the burglar must travel to get there. With this L is the larger jump allowed that we allow the criminals to move, and mu is the exponent of the underlying levy flight. The model is then described by these two equations. The first one I already talked about. These models repeat and near-repeat victimization and Brunken-Windus effect, and this is the criminal activity and where they are located and how they travel in the city. Some effects of L, some particular cases that we can recover from the model. When L is equal to 1, you have a random walk. The criminals just move according to a random walk. They just move one step up, down, left or right. But this could lead to a high number of small hotspots, such that the criminals are generated in some place. They don't have a very number of possibilities to travel to. They don't have a lot of knowledge of the attractiveness of the whole city, so they burglar someplace quickly and disappear again. On the other hand, if you have L equals infinity, burglars can travel anywhere they want. So this might be the case that they displace to some most attractive neighborhoods, generating some few aesthetic hotspots. So we use this L between 1 and infinity, this truncated levy flights model to get to the most realistic, in some sense, hotspots in Bogota. Well, this is the table of all the parameters what we need to estimate. In particular, we are interested in estimate this omega, the rate of decaying of the attractiveness. This theta, that's the factor a house increment its attractiveness each burglary event, and this eta, the spreading effect of the attractiveness. And we want to maximize the probability of obtaining a non-crime sample. We do this via log likelihood function, such that if a crime occurred in house SK at time TK, we want that this product n times A, that it's the expected number of crimes at that place, to be large, but not with an arbitrarily large number of expected crimes over the whole lattice. So we want that the crime data of houses still and times reflects this location of criminals and attractiveness perceived by them. The data set corresponds to georeferenced residential burglaries in Bogota from 2012 and 2013 from the Metropolitan Police, and it was trained with 6-month data, and its predictive accuracy tested with the corresponding following month. We use this grid cell of cells of 180 meters width and 320 meters height. The time step is 1 day. The levy flight is 2.5, and the larger jump allowed is of 10 kilometers. The 6 months training window was divided then into subgroups. The first 3 months was used to estimate this static attractiveness component and the burglar's generation rate, while the following 3 months were used to estimate the other parameters of interest using this maximum likelihood estimation. So gamma was set to the average daily number of crimes events in Bogota, such that we have a constant number of criminals in the city, and A0 was estimated through kernel density estimation to these locations of the crimes during these 3 first months of the data. Then the model evolves through these equations that I explained before, and we use maximum likelihood estimation to find the parameters omega, theta, and eta. In the test procedure, from the final states of the training process, the system evolves according to the same equation by replacing this E, that it was the number of crimes in the data, but it's probabilistic number of crimes, that is the probability of a burglar event in the house S times the number of criminals in that cell. And in each one of these time steps, the X% of the cells with a higher expected number of crimes are marked as hotspots, such that we can use this hit rate measure as the portion of crimes that occur in these predicted hotspots over proportion of the total number of crimes. We vary this X% of the cells. Well, if you marked all the city as hotspot, well, you will recover all the crimes. So you want to have some X value, like an optimum X value. So we use this cumulative accuracy profile. And here is the curve. On the X-axis is the percentage of cells flagged as hotspots. And with the Y-axis is the hit rate by the model. And we compare its predictive accuracy against the one model of kernel density estimation and the model of self-exciting point process. And these particular cases of L equal 1, L equal infinity, and L equal 10 kilometers. The result indicates that the predictive accuracy of the truncated Levi-Flight model is statistically equal to the kernel density estimation and the Levi-Flight model, but it's statistically greater than the random walk model and the self-exciting point process. But furthermore, we have this with these parameters that we have estimated and we can interpret. In particular, the decay rate of 0.004 evidence a long time span when repeat and near-repeat victimization has an increased likelihood of occurrence. Each day, the dynamic attractiveness component decays by 0.4%. The parameter theta equals 5.551 exhibits a bias of criminals to return to previously burglarized houses. If you do the math, this means that when a house is burglarized, the next day its probability of being burglarized again increases by 79 percentage points. And the triggering effects of 0.94 shows a strong and quickly spreading of attractiveness to neighboring sites. So each time a house is burglarized, the attractiveness of its neighbors also increment very quickly, validating broken windows theory and self-exciting nature of crime. So as a conclusion, these models well validates repeat and near-repeat victimization, broken windows theory, such that these mechanisms increase the probability of new crimes in a spatiotemporal neighborhood of an initial crime. These agent-based models elucidate criminal rationality without losing predictive accuracy against other state-of-the-art crime prediction models, and these mechanisms must be taken into account by public policies seeking to reduce criminal activity and its negative consequences. Thank you.
Thank you so much, Mateo. And we are a little bit ahead of schedule, so we can do a 5-minute break so that you guys can go to the bathroom, grab a water or coffee or whatever. And we'll continue at 5, like in 5 minutes, literally, with Juan Ramón Vallarta, who's coming from Mexico. And he's going to be talking about diabetes. So very interesting research. Thank you. So we continue in 5 minutes, okay? 5.
¿No la tienes?